it's Ross, your TA for statics, and welcome to my garage. Here I intend to do some miniature lessons and also go through a lot of the solvents you've been provided for the rest of the semester. Now I won't be doing every single solvent. My intention is to give some little miniature lessons at the board, and then we'll go over to my document camera, which is my phone on a microphone stand, and work some problems out on paper. I hope to hit all the major points, but if you have any sticking points, please just email me. I'll take requests. I can do individual little problems, but I'm going to try to do a Chapter 6 kind of comprehensive thing, and I'll timestamp all the different problems we go through, so if you're just looking for one thing or the other, you can just skip to it. So once you join me, Alright, so trusses, they're all over the place if you look for them. Very, very useful way to support a lot of loads with a lot less material and money. So, pretty much every truss problem, you're going to end up seeing there's going to be some kind of a pin joint here and some kind of a roller joint. It's either going to look like a roller skate or a little egg-shaped wheel. And even though it's not always necessary to solve for your reaction, your support reactions to start solving the problem and to find the internal forces of all the different members, you're always going to be able to. So that's one thing that we're going to see later on in frames and machines. Sorry, in machines it's a little different, is that you're not going to be able to necessarily just look at the whole problem and say, okay, here's the reaction forces to put this all into equilibrium. However, trusses, we can always do that. So if we were to subject this simple truss here to say, like, you know, a sideward load, that's a scientific term, then you can see that this whole, it's going to want to, it's going to cause a moment about this pin, and it's going to try to get the whole thing to rotate. And so the only way to counteract that, right, is through our support reaction. And here at our little roller skate, we can only have support reactions vertically. So we know we're going to be able to solve for a little reaction here. And then we've introduced this vertical force that's going to have to get counteracted somewhere else. Well, where can we counteract it? Only right here. So we know that we're going to have this other vertical force at the pin joint. Finally, there's this X component here. I mean, it's all X, this force. And that's going to have to get balanced out somewhere. So we're going to put that right here. So in like example 6.2, it's one of your solvents. Worked out in the book. You see, even though they're not both on the ground like we'd normally have, we've got our pin joint that's going to have an X and a Y support component, probably, and then we've got our little egg-shaped roller that's going to have a vertical support component. Okay, sorry, so we've got dimensions now. So you've got 400 newtons acting 3 meters away trying to turn this counterclockwise. You've got 600 newtons acting 4 meters away trying to turn it counterclockwise. Those are working together, so we're going to need to work against that here at this support. So 400 times 3, 1200. 600 times 4 is 2400. That's 3600. We've got to counteract 6 meters away, so there's going to be 600 newtons acting up like this. Okay, so now we have 600 newtons vertical, 400 newtons vertical the other way. What's left is 200 newtons this way. And then we've got 600 newtons this way. Nothing else happening in the X direction, so we know we're going to need 600 newtons here. So you can always find your support reactions before you go about solving. You don't always have to. We'll look at that in joint selection. But just know that with these truss problems, it's pretty much always going to look like this, where you have a pin and some kind of, rotation, and then a little wheel. Okay, so when we worry about trusses, we know they're always going to be two force members. This makes our lives much, much simpler. What do we mean by a two-force member? Well, if you remember from last chapter, it's just going to be a member where you have only the force in the direction of the member. It's equal and opposite at both ends. And so how do we get one of these? Well, here we've got a simple truss, and if we apply a force to a joint, so like this, and we're going to make some two-force members. All right, so we'd end up probably with, you know, so that's going to make this four here. It's going to make this, and it's going to make that, yeah. And so you see, we're going to end up with, you know, this one getting stretched out, this one getting squoze in, right? So you're going to have, you know, down here you'll be able to figure it out, but that looks like it's also going to be tension. Anyhow, what is not a two-force member is if we apply this load here in the middle. So, so that is, okay. This, all right, this is going to create some other kind of stuff that we're going to worry about when we get to frames. But this right here is not a two-force member because the load is not being applied to one of the joints, okay? And this load doesn't have to be applied like you know, horizontally. We could have it be, you know, vertically, but it's got to be applied at the joint. So this is not a two-force member. Okay, so these two-force members have two possibilities of what's going to happen in them, excluding zero force. I guess there's three. They could be in tension, they could be in compression, or they could be zero force. So if a member is in tension, the bar is getting stretched out. And so from the member's view, tension is going to look like this. You've got these two forces, each pin is pulling it apart. But equivalently, so let's go. Okay, so we have tension here. Okay, but if we look at the same thing from the joint's perspective, we're going to have the arrows facing the other way. That's Newton's third law, right? We've got each action has an equal and opposite reaction. So even though there's some confusion here sometimes, because you look at arrows like this, it's like, looks like they're pointing in, and it looks like they're squeezing that bar, which makes you think compression sometimes. But don't ever think that. What's happening here is that the bar is pulling in, it's tugging in at each joint, and so this is also tension. Conversely, if I'm the bar, compression looks like it's squeezing in on me. So we write C for compression. It's terrible. And then if you look at it from the joint perspective, this is the bar pushing out on the joints, and so this is also compression. So just make sure that you're always aware when you're drawing free body diagrams and trying to analyze joints or members that you know which one you're looking at, which perspective you're looking from, because this will start to matter a whole lot when we get to free body diagrams of frames and machines and things like that. Okay, like I was talking about just previously, sometimes a two-force member is actually a zero-force member. So this happens in two different situations. One situation is when the two members connect at a joint that is subjected to no external loading. Hold on. So one situation happens where you have a joint of just two of these two-force members. They're jointed a pin joint, and it's subjected to no external forces or reaction forces. So it can't be at one of your roller skates or your pin joints. It can't be acted on by an outside force. But you see that with this force happening here, this is being counteracted by these guys, and even if there's force, you know, being exerted kind of like oblique-like or whatever, this force is going to be compensated over here, because if there's no reaction force or external force happening over here, then there's really nothing that this joint could do to counteract some kind of a force developing in here. So this tells you that that both of these are going to be zero force members, and that you can just basically forget about them when you're doing. Oh, I ruined my red. Forget about them when you're doing your problem. Likewise, if you ever find a place where you have two members that are collinear, and then there's a third member joining that joint, then that third member is a prime candidate for a zero force member. And this is one that's kind of confusing at first, because you have, in like this situation, you have a force that appears to be applied directly into this middle member. However, if this member was to be counteracting this force, you know, imagining that these weren't there, then it would have to be supplying, it would have to be in compression to counteract that. And so down here, you would need something to counteract that compression. And there's nothing here. There's no reaction, there's no external force. So that tells you that all of the load from here is going into these guys, and then subsequently these guys, who have equal and opposite reaction forces in this plane, and then it doesn't leave anything left for this to do. So then this is also going to be a zero force member. Remember, however, if there's ever a load applied directly to it, all bets are off, and you got to analyze the forces in it now. This is now a load carrying member. All right, method of joints. It's always nice to be able to find the zero force members before you solve, so that you don't end up overcomplicating things or trying to solve a harder problem than there actually is. In fact, in some cases, they might make it so that you have to find these in order to solve the problem. But in this one, we're just worried about finding zero force members, and it's actually very easy to do. So remember, we have two different ways to tell if there's a zero force member. The first one is that there will be only two members forming a truss joint, and there will be no external load or reaction support load on it. So if we look at our diagram, there's E and A both have two members forming truss joints. However, both of them are going to have support reaction forces. E is our little roller, A is our pin joint, and with external loads on the whole thing, we know that both of these are going to have some kind of external loads. So these are not going to have zero force members. The next way is where two of three members are collinear. Then the third is a zero force member if there's no external reaction force or external loading. And so we have three places in this one figure where that is the case. We have joint D, where CD, DE are collinear, and DF is not, and we do not see any external loading on DF. So we know that DF is going to be a zero force member. We also see this happening here at G, where HG, GF are collinear, GC is not. So GC is the one we're concerned about here, and there's no external load being applied at G. Now this is one that'll confuse this force being directed straight into G here, and you just think there's no way that there's not some loading happening here. But then if you thought about if this 5 kilonewton load was running into this CG member here, then there would have to be something counteracting that in the Y direction, which we don't have. So we know that this segment GC here, CG, whatever, I'm going to have to get better at keeping that consistent, but we'll call it GC is going to be a zero force member as well. Okay, so another obvious one is going to be B right here, where we have these two collinear and BH is not. However, you see that there is an external load being applied directly at B, so we know that BH is not a zero force member. Okay? And now finally, the one that doesn't stand out quite as much, but still is the same, is right here. We see F. We have GF and FE are collinear. We already know that DF is a zero force member, and looking at FC, CF here, this one's also going to have to be a zero force member. Similarly to G, we don't have anything being exerted at F. So even though we're not seeing this nice little like right angle deal like we see in our perfect examples, we still know that that this is going to be a zero force member because we have no external loads being applied here at F. So then CF is also going to be a zero force member. And then these are the only three that we have. Looking here at F6-2, just says which joint are you going to start with. So the order that they prescribe is to first look for zero force members. So looking for, here, let's write it down as we go along. ZFM. All right. So we only have one situation where you have two-member joint, and that one does have an external load applied to it, so that's not gonna, neither of these are gonna be a zero force member. And then we have one situation where we have two collinear members here, meaning that the third one is a candidate for being a zero force member. So what we do is we look at the joint C where the three meet, and we say, is there any support reaction or external load being applied at joint C? And there's not. So remember that it doesn't matter that there's going to be a reaction force at A. We're interested in C here. And it tells us that because there's no external load here and these guys are collinear, then CA is going to be a zero force member. So now we want to look and see about our knowns and unknowns in this problem. And so you might be tempted to jump right away into looking at the into figuring out the support reactions at A and B, which is, you know, totally fine to do, and you'll probably end up wanting those if you're going to be solving for every different member in the problem. But we don't actually have to in this situation, because if we look at D right here, we see that we have our one known, that's this 300-pound force being applied in the negative y direction, and then we have our two unknowns in DA and DC. So this is actually a valid place for us to start. We've got our 300 pounds down here. And then this is also going to be one of those situations where we can figure out the direction of our forces just by inspection. Don't ever worry if you can't do that, because it'll always be able to come out in the positives and negatives as long as you make your assumptions correctly. But here we can see that given this 300-pound force negative, there's nothing that DA can do to counteract that, because it's in the x direction, it's perpendicular, there's no way it can exert anything against that 300-pound load. So that means that DB is going to have to be, it's going to have its y component in opposition to, and DB will be in tension, because it's going to be trying to pull that in. And then we see that if DB is in tension, it's going to create this this force in the x direction, positive x direction. And because the 300-pound load doesn't do anything in the x direction, it means that DA is going to be having to apply a force in the negative x direction, meaning that DA will be in compression. All right. And so, sorry about being off screen a little bit here. You know, I'm just getting used to this now. So if we want to start solving here, we can look at the summation in the y direction equals 0. And so we know that this guy up here is going to be 5 feet, because it is a 3, 4, 5 triangle. So what we can do, all right, so 3/5 of FDC is 300 pounds, which means that FDC is 500 pounds, and that is going to be in tension, as we discussed. And knowing that, we can use our summation in the x direction equals to 0, and that's going to say that 4/5 of FDC, 4/5 of FDC minus, excuse me, golly, 4/5 of FDC minus FDA is going to equal 0. So we get that FDA is going to be 400 pounds. And that one is in compression, as we discussed. All right, and from there, the rest of the problem is, you know, the same stuff going at the joints. Alrighty. Okay, moving on to 6-1 here. Same thing. We're going to look for the joint choice. We're going to look for the joint that we want to start at. And so, per the recommendations of the book, first we want to look for some zero force members. Only two that have two members joining at a joint are both going to have support reaction forces at them. So we know it can't be either of those. And then we look for joints where there's at least two collinear members. So we have one here at B, because AB is collinear with BC, meaning that BD is potentially a zero force member, and we see that there's no external load acting on it. Sorry, this is just for like the 4 feet kind of thing. This is not a load, my bad. So we see that without any external forces acting on B, that DB is in fact a zero force member. So you can just kind of like, not think about that. Looking at support reactions now, we see that this 450 Newton force is sort of tending to rotate this whole thing about C, right? And so that means that we're going to have a reaction force here called AY. And if we've got that, then that means we're going to have a reaction force down here called CY. And then if we've got this guy here, it needs to be balanced out by this guy here. That's going to be CX. Okay. So we have a few choices here, but I think that A is going to be the one that's going to be the easiest for us to start at, because we'll know this AY in a sec, and then this AB is in the X direction, so we're going to be able to directly solve for this AD very easily. So first we have to find our support reaction, so this whole thing is tending this way, so we're going to balance out the moment about C. So we see that summing in the counterclockwise direction, our moment about C is 0. And we have counterclockwise 450 pounds applied 4 feet. Sorry, I was saying newtons before. So we've got 450 times 4 feet plus AY times 8 feet. Sorry, it's gonna be minus AY times 8 feet. Should equal 0. That gets us AY equal to 225 pounds. Okay, so now that we know AY, we can solve for AD by looking at, let's just draw joint A here. All right, so we've got 225. We have, because we have this 225 pounds pushing straight up, then we know that this component vertically is going to have to go down, so we know already that AD is going to be in compression, and so because that's going to be in compression, it's going to have an X component that's going negative, meaning that we'll have to balance that X component out with a positive one here. So we know that AB will be in tension. All right, so now doing our summation in the Y direction. For joint A, we have 225 minus AD. This is 45 degrees because we've got 4 feet and 4 feet. So AD, cosine or sine, doesn't matter because it's 45. I really should write sine just so that it's kind of, consistent with the fact that we're going in the vertical direction. Sine 45 is going to equal 0. And what we get is that AD 318.2 pounds, and that is compression. So then in the x direction, we get that FAD cosine 45, we'll say this time, which, spoiler alert, is 225. FAD cosine 45, we'll call that minus because it's going that way, plus FAB, which is already in the x direction, is going to equal 0, and what we get from that is that FAB equals 225 pounds in tension. Okay. So that's how we'd start this problem off, and so that shows us that we've got this here, we've got this compressive load here, meaning that we've got that same kind of deal going on there. We know about our tension here, which is going to equal our tension here, which equals our tension here, which equals our tension here. CY has to get balanced out by CD. And if you do that summation just like we did down here, you're going to get that this FCD equals 318.2 pounds. And it's just going to be in tension instead of the compression that we saw in FAD. All right, example 6-1, just about the easiest. My neighbor has a chicken. Don't mind the chicken. I'm doing this out in my garage. All right, so we have this very simple truss, 45, 45, 90. We've got a 500 Newton load being applied at joint B up here. And let's get to solving. So first off, we look for any zero force members. Though these are all joints of only 2 members, this one has an external load, and these two have support reactions. So there's not going to be any zero force members. So then we can go ahead and draw our free body diagram. We see that this 500 newtons at B is going to create a moment about A, and so we're going to need to counteract that moment here at C. So there will be CY, and then that vertical load CY is going to have to be counteracted at A. Give us our AY. And finally, 500 newtons in the positive x direction is going to need to be counteracted by 500 newtons, in the negative x direction. And we'll call that a x. All right, so there's our free body diagram. I know I drew it over the original diagram, but I spent time with a ruler to make that, so I figure we'll use it. All right, so now we want to get to solving, and we look at what we've got going on in the different joints, and we see that if we did go ahead and calculate AX, AY, and CY, then we could start really wherever we wanted. But let's go ahead and skip that, because we can see that at B we already have 1 known and 2 unknowns, and so we can just go ahead and get to solving. So let's draw joint B. So we have 500 newtons being in the positive x direction. And then we can tell, because we only have 1 member of the 3, one force here that would be able to counteract that x direction is going to be this BC member, because there's no x component to BA here. There's no x component, so we know that BC is going to be it's going to be in this direction, and that indicates compression. However, because it becomes very useful later on in more difficult problems to make assumptions and then, see when the answer comes out whether it's positive or negative to support or deny that or refute that assumption, we're going to go ahead and assume that this one is in tension. We're going to assume that We're going to assume this is in tension. Assume that this is also in tension. And then just watch what happens here. So this is our FBC, and this is our FBA. All right, so let's sum about joint B in the x direction. So we have 500 newtons. Adding, because we're assuming this is in compression, so it's x direction is that way. So we're adding this FBC times the cosine of 45, and that's going to equal 0. Okay, and so when we do this, we get FBC equals negative 707.1 newtons. So because we assumed it was in tension and then we ended up with a negative for the answer, that means that we're going to reverse this, and we'll say, sorry, too many arrows, it might be confusing. We're going to say this is 707.1 newtons in compression. Okay, and so now that we know that one's in compression, that does confirm that our FBA is going to be in tension, because the Y component of FBC is going to be in the vertical direction, the positive Y direction, meaning that the FBA is going to have to be in the negative Y direction. So let's go ahead and do that. Summing the positive FY. We get 707.1 times the cosine. I guess here, if you were looking at that 45, then it would have made more sense to use sine of 45, but again, since we're using 45 degrees here, it does not matter if we're cosine or sine. So 707.1 cosine 45 minus that FBA equals 0. And what we get is that FBA is going to equal 500 newtons. And that is in tension. All right, moving along. Let's go ahead and look at joint C now, because we know what this is, and so we've got, at this point, two knowns and only, well, okay, so we don't know CY yet because we decided to skip the support reaction thing. But watch how easy this is going to be. So at joint C, we have FBC, which is 707.1, and we have CY. And so based on the direction of FBC here, we see that FCA is going to have to be in tension. So let's go ahead and sum in the Y direction. they're going to be equivalent because of this 45-degree thing. So this is equal to 0, and we're going to get that by saying SFBC. Sorry, we know FBC, so we'll say 707.1 sine 45 minus 707.1 sine 45 is coming in this way, plus CY equals 0, and we get that CY is 500 newtons. Exact same thing happens for summation at X. We get that 707.1. We'll say cosine this time. 45 minus FCA. It's going to equal 0. And then we get that FCA equals 500 newtons. And that will also be in tension. Okay. So, all right, example 6.2. This is a pretty good one for practice, I think, because it has the, you got to do some concurrent solving and whatnot. And it's also just kind of a funky looking truss. Not quite as easy to figure out what to do right off the bat. But anyway, we're going to do that. So looking at it, we don't see any zero force members, and we also see that we are going to need to find the support reactions before we get on to solving any further. So we see that that 3 kilonewton load is going to be causing a moment about A, that the roller joint, support roller, what do they call this? Little roller skate on C is going to be counteracting with a moment that looks like this. I mean, a force that looks like this will be giving the moment that counteracts this moment. So that's going to be CY. And in order to oppose CY, we're going to need an AY like that. And to oppose the 3 kilonewtons, we're going to need an AX like that. Okay. So let's figure out what those support reactions are equal to. So summing moments about A with counterclockwise is positive. We see that that 3 kilonewtons is generating a negative moment about A from 2 meters away. Line of action goes to 2 meters here. So we have minus 3 kilonewtons times 2 meters plus CY times 4 meters, as 0 gets us CY equals 1.5 kilonewtons. Okay. If CY is 1.5 kilonewtons, then we know that in our Y direction, basically CY and AY are going to be equal because there's no other external loading in the Y direction, so we can just say AY equals 1.5 kilonewtons, but remember that's downward. And similarly, summing up our X's, we get that AX is going to have to just oppose this 3 kilonewtons. So it's going to be 3KN minus AX equals 0, and AX equals 3 kilonewtons. Okay, so far so good. Now, looking at the next steps we can take, we know at C we have 1 known and 2 unknowns. So we're going to go ahead and start at joint C. However, what separates this from previous examples is that because we don't have one of our members directed along the X or Y axis, we're going to need to do one of 2 things. We're going to need to either solve a system of equations, of 2 equations, or we're going to need to change our axes. So I'm going to start out by doing the change of axes, actually. So what we have at joint C is this CY. CY. We've got FBC coming in at 45 degrees. This is FBC. And we have sorry, FBC. We're just going to go ahead and draw them in tension for now because we're just going to be making that assumption like the book says to do. And here's CD. Okay, FCD. And so our original x-axis looked like this, where FCD was off it by 30 degrees and FBC was off it by 45. So if this was 30 degrees, we're going to make FCD our new x-axis. So now, coming across here, so this was x. Now this is going to be x prime, okay? And then perpendicular to x prime, we have y prime. All right, so now we have to just make sure that we understand what our components of each of these things are going to look like in our new x prime, y prime configuration. So FCD is directed along the x prime axis. FBC, this angle between CD and BC, is 15 degrees. 15 degrees, sorry, that's terrible. 15 degrees. This is pretty small, guys, I'm sorry. But, so that angle there is 15 degrees. And then between CY and BC, this is that 30 degrees that we shifted everything. Okay. And so, all right. So now, the reason we moved it into this new coordinate frame, this new coordinate system, is so that FCD disappears when we want to sum about the y prime axis. So let's go ahead and do that. Say, now it's kind of janky and pointing like that. So summation about y prime is going to equal 0. And so now that equals the y prime component of FBC, which is going to be FBC times the sine of 15 degrees. And remember, because we're assuming tension, we've got that going positive. Plus CY times the cosine. See, because this 30 is here, so the cosine is going to be this component. Sine is going to be this one. CY times the cosine of 30. Equals 0. And we know what CY is. We know CY equals 1.5 kilonewtons. Sorry about that. All right, and so what that gets us is that FCBC, we're calling it BC here, FBC equals negative 5.02 kilonewtons. And so because we got that negative and we were assuming it's in tension, that means that FBC is positive 5.02 kilonewtons in compression. Okay? And then now we can do the summation of the x-axis, so the x prime axis, I should say. So that's kind of pointing like that, sort of. And you know, this is where it's kind of nice to do your little arrows before your summation symbols, just to remind yourself what's going on. Of f x prime is going to be minus FCD plus the sine component of this, or that guy right there, which is going to be cy sine 30 which equals 0. cy was 1.5k again. And that gets us that FCD is equal to 4.1 kilonewtons. All right, and so, and that stayed positive, so we can confirm our assumption, our guess, that it was going to be in tension. Okay, so we did this change of coordinates in order to be able to solve directly instead of solving equations simultaneously, but all right, so it's not too hard to solve a simultaneous system of two equations, but I'm going to go ahead and use this opportunity to demonstrate doing that with one of your, trusty TI calculators, because I think this is something that's going to be very beneficial to those of you that don't already do this. I think you can save a lot of time on tests where you can just enter in the equations and get your answers instead of having to think at all about how you want to do your elimination or substitution. So even though this is probably a pretty trivial example to be doing it with, I think it's a good skill. So you can just skip ahead if you're not interested in this part. But basically, a system of equations, when you write it in, well, let's develop our equations first real quick. All right, so we are just using the regular x and y axes this time, not the changed coordinates that we did last time. Okay, so whenever we solve a system of equations as a matrix, a linear system of equations, I should say, so we set these things up as ax equals b, and then the solution can be calculated if you just do a inverse times b equals x. Okay, and so what a ends up looking like is the coefficients of your x and your y. We'll call BC is x, CD is y. Your b is what they equal. So that's going to be your 0 up here, and it's going to be minus 1.5k over here. So basically, our A matrix will be here, and so we have minus FBC cosine 45. So let's just write minus cosine 45, because that's our coefficient for FBC on our first equation. And then we have minus cosine 30 here. Okay, and so that equaled 0. All right. And then we've got our sine 45 down here. And our sine 30 down here. And then this is our FBC, and this is our FCD. Okay, so this is the A matrix, this is the X matrix, or vector or whatever, and then this is our B. And as you can see, we're going to need to account for our 1.5 kilonewtons. We're going to subtract it from both sides, so we're going to end up with minus 1.5k over here. This column is going to be your FCB, and this column is going to be your sorry, I said BC, didn't I? BC, and these ones are your FCD. And what you're going to get back when you put it into the calculator is A inverse times B. Your X is just going to come back and give you what FBC is and what FCD is. So, getting at your trusty TI 84 plus, oh man, living large here. We go second, matrix, edit, it's a 2 by 2, right on, get minus cosine 45 we get minus cosine 30. We've got sine of 45, and we've got sine of 30. Right on. Okay. Now we're going to edit this one, and we got 0. This is our b. 0. And minus 1.5. Well, let's just go ahead and write 1500. No, let's keep it in kilo. All right, cool. So now what we do is we just go matrix A, okay? What we're doing right now is this, by the way. A inverse B. Look at that. So, move that there. So our A inverse times B equals X, which equals minus 5.02 and 4.1. Okay. And this was X, which is equivalent to our FBC and our FCD. So I know it took me a little while to talk through here. I apologize, I'm not so used to teaching, but the moral of the story is you can kind of chug through these systems of equations in your calculator without ever thinking about them. And particularly whenever you get to a system of 3 equations or more, this is by far the best way to go about doing it. So anyway, we see that we got our negative here, our negative 5.02, which meant that our assumption about the tension was incorrect. So we say that FBC is 5.02 kilonewtons in compression, and that our FCD was correct as 4.1 kilonewtons in tension. All right, moving right along. Now let's take a look at joint D. All right, so you can see I've already drawn the directions of all of them. And that's because this particular joint, you can actually kind of be a little clever with this one. So for FDA and FCD, it's pretty apparent that they're going to have to be their X components. They're symmetrical, right, about the y-axis. So they're just going to be equal and opposite. But what you can realize about this whole thing is that you've got 60 degrees between every single pair of these, right? Okay, so we can see by the radial symmetry here how these are all going to have to be the same tensile force. So FDA is equal to FBD is equal to FCD. And those are all equal to 4.1 kilonewtons in compression. In tension. We can turn that into a T, can't we? Kind of looks a little towy. All right, that's good. Okay, and then we'll got one more before we go, which is to figure out what this force AB is going to be. So we'll go ahead and take a look at, it doesn't matter if we do it at A or at B. Let's just look at A because we've only got, well, let's look at B. Let's look at B, I like that. All right, so let's see. All right, we'll just assume tension like we normally do when we're assuming. And if we sum in the X direction, the X, what's going on? Okay, positive. Fx 0, which is going to be 3k minus 5.02 times, minus 5.02 sine, or cosine, or whatever, of 45 minus FAB cosine 45 equals 0. That gets us FAB equals minus 0.777 kilonewtons. And that was because we assumed it was in tension, so we know, no, that was wrong, that it's in compression. So that says FAB equals 0.777 kilonewtons in compression. Okay. And that is it. All right, so phone had come unplugged and it died while I was filming this, so I'm just going to be kind of revealing some of this as I talk about it. But we're into space trusses. We're trying to find the forces in all of the members, so we want to use method of joints just like we would in planar trusses. So basically what we see here is this kind of, well, I mean, it's a tetrahedron like you're pretty much only ever going to see in these space truss problems. But you can see that it's kind of, you know, this weird skewed pyramid deal that sort of fits within this 2 by 2 by 2 kind of cube. Anyway, we can see these support reactions at C, D, and B. The one at B is kind of hard to tell what's going on there. But basically, it's in the XY plane. The support reaction at B is. It doesn't have any Z component to it, and it's 45 degrees from both of those. So, anyway. Then E is the one where it's like welded. So that basically just means that at E you can have these support reactions in 3 directions. It's the equivalent of those, like, you know, pinned down ones, whereas these are kind of the equivalent of rollers. So I went ahead and already got the unit vectors for AE, BE, and CE because those are the only ones that aren't simply along one of the coordinate axes that's already defined. So like, you know, CD, that's just going to be multiplied by the J unit vector, and AC is just multiplied by the K unit vector, whereas these are going to have to be multiplied by a few because they're Cartesian vectors now because we're in 3D. All right, so we're going to start at A because, and forget about that little arrow there. We're going to start at A because we have 1 known and 3 unknowns. And in 3D space trusses here, we can do that. So we're just going to write out that, you know, the vector notation for each of these unknown forces. So FAB is FAB in the J direction. FAC is FAC in the K direction. FAE is FAE in this 0.577 yada yada direction. And then P is this minus 4 kilonewtons in the J direction. Okay, so we're just going to go ahead and sum up forces equal to 0. But it will kind of end up making a system, but the way this problem is set up and the way that space stress problems are generally going to be set up, it'll just kind of reveal things as it goes along. So Fx is going to be this 0.577I that you get for this FAE I component, and nothing else. So that tells us that the entire vector FAE is going to be equal to 0 because this is not just saying, oh, this, you know, it's saying the whole FAE times 0.577 is equal to 0. So we know that FAE, this long guy, is going to be a 0 force member. Okay. I'll actually box that. Now summing in the y direction, we have this minus 4 kilonewtons plus the FAB in the other direction. we're assuming it's in the other direction because that really seems like it's going to be the case, plus the FAE in the j direction, which we just found out was equal to 0, so we can cross out the FAE in the j direction, and then we just get that FAB is going to be 4 kilonewtons. And so it's 4 kilonewtons in the positive I direction, but unlike we were doing in previous units, we're not just going to say positive 4 kilonewtons, we have to say it's 4 kilonewtons in tension, because when we get over to B, that's going to be in the negative j direction. So don't get confused based on what we've done in previous units. You still have to consider each of these as a two-force member, and each of them is going to have either tension or compression, which will be positive for one end and negative for the other end. All right, and then for FZ, we have FAC minus the Z component of FAE. We still have FAE equal to 0, so our FAC is also going to be 0. So this is a 0 force member here, this is a 0 force member here. All right, so now we can move along. Let's go ahead and take a look at what's going on with B. So we have that 2 kilonewton in the positive Z direction. We have our known force AB, and then we have unknowns for BE, BD, and the support reaction, which we're going to call RB. Okay, so here's a drawing of it. Kind of crude, but this is RB back here. BE, BD, 4K, and 2K. So I'm just assuming here, that the BD force is going to be in tension, just like we've done when we don't know for sure. Looks like it might be. Same with FBE. So we're just going to roll with that and see what happens. All right, so we have this 0.707 FBE minus our RB cosine 45 is 0. So we know that RB and FBE are going to be the same magnitude. We have FY, a lot more going on, not a lot more going on, some more going on. So we have our RB in there, sine 45, and then we have 4 kilonewtons from our FAB that we know. So then that helps us figure out what RB is, which is 5.66 kilonewtons, and we learned from here that that was going to be equal to FBE. So sines came out positive, so sorry about that. 0.66 is kind of ugly, but we get that FBE is 5.66 kilonewtons in tension. All right, we move along. We find FZ. We've got 2 kilonewtons minus our FBD that we're assuming is in tension, minus 0.707 FBE. We found out what FBE is. We can plug that in. It was 5.66, okay? And that's going to equal 0. So then we get that FBD is minus 2 kilonewtons. And so that told us that our assumption about tension was incorrect. So we're going to write FBD is equal to 2 kilonewtons in compression. All right. So now, we're back to where I left off last time. We can keep on chugging. And let's take a look at joint D. So we have BD, which is in the vertical direction, and we know that it's 2 kilonewtons, and we also know that we have this directional support here that can only support in that positive Z direction. So we know that BD is just going to be reacted by this. CD has nothing that it's going to react with, so CD looks to be a 0 force member. Here, I'll just write ZFM. So CD. Recall we had some other 0 force members as well. We had F8, we had, sorry, this is FCD, okay. 0 force member, we had F. FAE is also zero force member. FAC was also a zero force member. Okay. Man, I've been bad about boxing these things. Okay. We have... All right, and then one more at this joint is going to be this DE. And again, we have nothing nothing acting here to cause any sort of loading in DE. So DE is also a zero force member. So this is where it kind of gets a little like, you start to think about like, okay, so FBE had actually had you know, a tension going on in it. And so you're thinking that like DE should have to have some tension, but really since this E is that like welded joint, then E can have a support reaction that's oh sorry, it was in tension. E can have this support reaction here that's counteracting that, and then the rest of these three can be zero force members, and they are. So yeah, so finally FCE, we had, this was a zero force, this was a zero force, and there's nothing different about this. It's another zero force member. And so you're done, and it turns out that the only three members that carried any of the tension in this problem were FAB, FBE, and FDB. Okay, so in the method of sections, what we want to do is solve for less than all of the different components, which in a small little situation like this, if you were, I don't know, building a bridge for like a footbridge for the park or something, or even a train bridge that only had a few members to it, doesn't make a whole lot of sense, but obviously in engineering sometimes we deal with much bigger, more complicated problems, and it helps to be able to kind of separate them out into little blocks. You see this in circuits when people have like an equivalent resistance, and so that some team can work on one block of things and just pass on the input and output to the next team, and they can learn stuff. So maybe you wanted to get the guy who has to get the person who has to source the material for the bolts, the kind of information they need. You might just section off some part of the project or something. I don't know. It's enough justification. In this class, what they're going to do is ask for a few different members of a bigger truss that are all arranged in a way that makes you think, oh, I should maybe just cut this and use the method of sections. And that's what we're going to do here. So we want FGE, FGC, and FBC of this truss, for which we've already found some support reactions. We didn't find this support reaction, but we don't even need to, because we're going to cut it off here, and we're going to just look at this left side. So that's what we have down here. And so these dotted lines are the other side of our cut for the three different unknown forces that we want to try and figure out. So what you end up doing in the method of sections is leveraging usually moment, by finding places like C and G here where two of your unknowns intersect an axis of rotation so that you can solve for whatever the third one is. So let's look at the moment about G. We'll sum counterclockwise per usual. So it's going to equal 0. And that's going to be, we have a clockwise moment from both of the reaction forces, so it's going to be minus 400 times 400 times 3 minus 300 times 4 plus our BC. We're adding it because we know that it's going to have to go counterclockwise to counteract these support reactions. So that's BC times our 3. So FBC times 3 equals 0. And what we get is that FBC is 800 newtons. And like we were saying, that BC is going to cause a counterclockwise moment, so it's going to be directed like so, which is tension. It's 800 newtons in tension. Okay, so now we can do the same exact thing here at joint C, where GC and BC are going to be eliminated. And so we'll be able to solve for GE. Okay, and so we have our 400 Newton force goes through the line of action, so that's not going to, or through the axis, the point, so that's not going to contribute. So all we have is this 300 newtons, that's 4 plus 4 meters away from C. So we have, and that's also going to be counterclockwise, so this is going to be minus 300 times, minus 300, yikes, times 8 plus our GE, which is going to be causing a counterclockwise rotation. So it's going to be directed that way. Go ahead and draw our arrow for it. Yeah. So that looks like compression to me. So that's plus FGE times, what do we have? 3 equals 0. So FGE is 24 over 3, also 800. FGE equals 800 newtons in compression this time. Alright, so FGE, since it has components in both the horizontal and vertical directions, we could sum it in the X or the Y if we wanted. Let's go ahead and use the Y, so summing in the Y. 0, and all we have is 300 newtons minus, this is a 3, 4, 5 triangle, and we want the 3 leg of it, so 3/5 times FGC equals 0, so FGC is 500 newtons. And because it has to counteract this positive vertical force with a negative one, we know that that's going to be facing this way, which looks like tension. And that's the method of sections. Alright, so here's a method of sections problem that's a little bit more complicated than some of the other ones. But it's a good example of a way that you can be clever and do a lot less work than it seems like the problem entails from the question. So the question we're asked is to find CD, I have CF. So that's all we want to get, is only this force right in here. And so knowing what we normally do with our method of sections, we're going to want to cut along here and then use the section that has fewer forces going on. But first, before we can section that off, we're going to need to solve for whatever unknowns for the reaction force here. So all we need to do then is to sum the moment about A to get that reaction force, because the other reaction forces are going to happen at A, and we don't care about A because we're going to take this right side of the problem. So all we got to do is sum the moment about A. We've got our minus 5 kilonewtons. That's 8 meters away. We've got our minus 3 kilonewtons, that's 12 meters away, plus our reaction force EY, that's 16 meters away. That comes out to being a positive vertical force of EY equals 4.75 kilonewtons. Okay, so now we'll section it off. We'll make our cut. And so you can see we have just this 4.75 kilonewtons, this 3 kilonewtons, and then we've got our 3 components. This is the one we're interested in right here, CF. And so normally what we would want to do here when we have our little square trusses is that we look for the places where, you know, like C, right, we'd be able to get GF here because C and D both intersect here. So if we summed our moment about C, then we could try to do our GF thing. But we can actually go straight to CF, even though it doesn't look quite as obvious here, by extending out this line GF and finding where it intersects with CD, and then summing the moment about wherever that point ends up being. We're given enough geometry to figure that out, because we see that this up here is a little 2 by 4 triangle, right? And so in order to get another 4 meters down, we're going to have to go down another 2, over another 4, down another 2. Excuse me, yeah, sorry. So we go down 2, over 4, down 2, over 4, down 2, and over 4 more. And this is going to be point. Let's just call it N. It's a new point. No, let's not call it N. That means newtons. Fine, we'll call it O like the book. Okay. So I'm just going to go ahead and draw that so that it's easier to visualize. Okay. So you see now we've got this big line of action for GO, or this big intersection of CD going all the way through to O, and GF going all the way through to O. And so if we want to sum moments about O, then we'll be able to solve for CF here, because we're just going to have this 3 kilonewtons, this 4.75 kilonewtons, and then whatever CF is here. Now, if we try to apply CF up here, we're going to have to do just a little bit of trigonometry, because this is not a perfect right angle with the axis. It's a 45-degree angle, and it's intersecting this 2 by 4 thing, which is, can't do that in my head. But what we can do to make this a little easier is just think about C down here. And now what's nice about this method of sections is that even though we see this 5 kilonewton load applied up here in the original problem, we've cut that off and we don't need to worry about that right now. For this sum about O, since we're maintaining equilibrium on this right side of things and we're not worried about the left side of things, then we can just take this, since it's a two-force member and there's going to be equal and opposite reactions at each end, then instead of having to do our little trigonometry thing here, figuring out that angle, then we can just take the vertical component of C down here that's 4, 4, 4, that's 12 meters away from point O. Alright, so the only thing we need to do is sum our moments about O, applying our CF load here, and we'll get our force in CF and we'll be done with the problem. It's that easy. So let's just counterclockwise, summation about O, which is going to be 4.75 moving clockwise times 4 meters plus 3 kilonewtons, 8 meters away. All right, and then that's bigger than that, so we know that we're going to have to subtract FCF. Remember, we're applying FCF here, right? And so if we're subtracting, we're saying that the vertical component of it is going to be down like so, which means that FCF is going to be compressive force. All right, so FCF, sine 45, applied 12 meters away, and that's going to equal 0. And what we get is that FCF equals 0.589 kilonewtons, and that's compressive, and we're done with the problem. So this is a great example of how a method of sections is really useful to do a lot less work. If you're in a crunch for time on a test and you're able to be clever about the way that you section it off, and this moment summing and moving CF down to here, you realize that you can boil it down to basically you only do two little equations instead of 12 or something. Alright, so finally we're looking at frames and machines, and this is kind of going to be bringing in stuff that we've done in the previous chapters and sort of meshing it with the things that we've learned about trusses so far. So really the name of the game when it comes to frames and machines is free body diagrams, and then more free body diagrams, and then after that you would do some free body diagrams. So what happens in a lot of cases, and we'll see this in some of the problems we're going to work on the ping pong table, you'll need to analyze different parts of a problem from different members' perspectives. Say like you have pulleys on a bar, you might want to look at the bar, you might want to look at the pulleys, and you know, always keeping in mind Newton's third law, that there's these equal and opposite reactions, and that's going to help you get through it. Second point, example 6.9 is awful. I hate it. Don't do it. Maybe look at it a little bit and see why maybe I hate it, but I think that the directions of the support reactions in it are just more confusing than anything else, and if they wanted to give an example like that, they should have put some numbers in it so that it would make a little bit more sense why the different ones are faced that way. Maybe I'll make like a 6.9 like vengeance video or something, but I've got a different one, a different example similar to that I think would be a much more illuminating thing to look at. And finally, look for two-force members whenever you can. That's going to simplify solving your problems a lot. So I'm just going to briefly go over this. I'm not going to like full solve it, but this will demonstrate that. This is example 6.14. So basically you've got this 2,000 Newton force acting in the middle of member BC. So you know this can't be a two-force member. But what's going to happen because of this is you're going to have a support reaction on either side. You're going to have CY here, and then you're going to have this UI here. And as you can see, this is loading at the joint, and then this is only going to be loading at the joint. And so BA is a two-force member, which is nice because that means that you're just going to have either tension or compression, and it's going to be equal and opposite, and it's going to be along the axis of that. So if we draw that out, if we break it out now, instead of trying to solve it all in one, we're going to look at the free body diagram of BC, and then we're going to look at AB. So we know that this force, since it's a two-force member, is going to be in the direction that's 60 degrees, right? So this is our support reaction, whose Y component is going to be balancing out this 2,000 newtons. We could do the whole, we could do all the summation, but you can see here, since this is 2 meters and 2 meters, that you're just going to have 1,000 newton support on both sides. So 1,000 newtons, 1,000 newtons. And then, so that means that this is a 30, 60, 90, I think. Yeah. All right, so basically this FBA, where do I write it? FBA is going to equal, that is 1,000 newtons, not 100. Sorry. Okay. FBA cosine 30 or FBA sine 60, whatever you want to say. We'll say FBA sine 60 is going to equal 1,000. And that gets you that FBA is something like 1,500 something or other. And then you're basically done, because now you have this, just this X component is going to have a reaction here. Right, so this is CY, CX, and then here, right, so if FBA is pushing on this, then that means that FBA is pushing on either side of it, so it is in compression, because those are pressing in on it. So, from the other side of things, you see this FBA right here, and right here is going to be equal and opposite, and so you're going to end up with a little, this is going to have your components here are going to be your AX and your AY. And so you can see how breaking it up and doing these multiple free body diagrams is going to illuminate the path forward, and especially that since you found the two-force member here, simplified a lot of things. They show you in the book how it's like several equations longer if you don't notice that this is a two-force member. So always look out for those. Don't trip about example 6.9, and we'll go work some more problems on the table. All right, so one final note that'll help you with your frames and machines part is that there's going to be a lot of pulley problems, and they tend to make things look pretty complicated with ropes all serpentine through the problem, but really they're not so bad at all. The main thing is that in a given rope, there's only going to be one tension, one tensile force. If they hang a mass on one end of a rope that's 75-pound force in that rope, then the entire rope is going to be carrying that 75 pounds of tension. It's basically, I don't want to say that. It's kind of like a two-force member that bends. That's not right. Anyway, we're not talking about bending moment. Anyhow, so if you have this tension here, that's they might hang a mass here, and then it might be hooked into a little eyelet here. That's not a person. That tension is continuous throughout, and those two tensile forces are going to add up, and the reaction force up here, we'll call this Ry, is equal to 2T. Okay, it's that easy. You've got 2 T's going down, you got Ry going up, is going to equal to 2 T's. Now, when you have your pulley going with a rope, in the Y direction, and then the other end of the rope is going in the X direction, then the reaction on your pulley pin is going to have an Rx and a Ry component, right? So this is Rx equals T. This is Ry equals T. Okay? And now finally, they get a little cheeky, and they try to go, somewhere in between. Somewhere in between them both being down and then one, both being out there. So what they do is they'll put a little theta in there, and you got to know that once you've introduced any amount of that, it's like whenever you have a two-force member that's any amount off of the perfectly on the X or Y axis. All right, free body diagrams. So this one wants us to draw free body diagrams for the frame, which is talking about this long rod, and the cylinder. So what we've got here is the cylinder that's working as a pulley because it's got this constant tension belt around it. Notably, that one's off at an oblique angle. And then we've got this mass, this weight that's yanking down on it over here. All right, so if we're supposed to draw a free body diagram of the pulley and of the frame, what I'd like to do first is the pulley because it's just simpler. There's fewer things going on with it, and then that'll help us develop the next one. So just draw our pulley right here. So we've got tension going this way, got tension going that way, and we've got theta. All right, so they show that this is both T, but really in any pulley problem, even if they only gave you this T and they didn't label that one, you'd know that this is also T because you have constant tension in all of it. So what's different between the two sides is that this one is going to have an X component in addition to the Y component. So this one's that T is all going into the Y direction, whereas this one has only a portion of it going in the Y and some of it going in the X. But we're here to draw a free body diagram, which means we have to balance these out. So we know that we're going to have this reaction force, we'll call it By. And then we know that we're going to have this reaction force, call it Bx, because that pulley is yanking on, that belt is yanking on the pulley in the negative X direction. All right, and so if you did have to go on and solve this, you would know that you would take Bx would be equal to the sine component. It would be, T sine theta, and then By would be this T plus that T cosine theta. So T plus T cosine theta. This isn't part of the problem, but in case you wanted to know. All right, and so then if we look at A, we've got... Okay, so now we can take what we learned from the pulley and look at the equal and opposite reactions it has on the frame right here. So By is yanking up from the frame's perspective. All right, and Bx tugging that way. That means from the frame it's going to be going the other way. And we'll just make that Bx. How convenient. Cool. What else do we have? We have weight pulling the frame down from the end. That's W. Okay? So now we just have to balance that out with reaction forces at A. So Bx is going that way, so we know we're going to have an Ax. And then this weight is talking about Y. We're going to have a negative AY here so that there's no moment. And that's the whole problem. The one more free body diagram you could draw on this problem if you wanted to would be, so this is one. That's the pulley. It's another, that's the frame. If you wanted to draw the free body diagram of the weight, okay, it would simply look like this. We can call this WY or something. I mean, it's just W, but it's equal and opposite that guy. And that's the whole free body diagram. All right, free body diagrams. We've got pulleys on a frame, and it wants 3 different free body diagrams. It asks for the frame and pulleys and cords. It asks for the frame without the pulleys and cords, and it asks for just the pulleys. Now, it seems like that's asking for most of the information first, but it's really not, because this free body diagram of the frame and pulleys and cords is actually pretty simple. Because if you think about it, you're going to leave all of this stuff in, and the only things you're going to have to take out are going to be your support reactions, right? So you just take out D and A, and you end up with something that looks like this, all right? And so to complete this free body diagram, all we have to do is replace D with a tension. It's a pulley, it's always going to be in tension. We'll just call that T, I guess. And then support reactions at A. So we've got 75 pounds yanking down. We're going to have to support that upwards with AY. We got tension in the positive X. So we're going to have AX and the negative X direction. All right. And it's that easy. Now I'm actually going to skip B for now and go straight to C, because the pulleys are kind of, I feel like it's easier to do the pulleys and then go back and apply those to the whole frame like we did in the last problem. I just think it makes a little bit more sense to do it that way. So let's go ahead and draw our pulleys. So we'll do B first. All right, so it's got 75 pounds hanging down. And since tension is constant through these pulleys, you know that this one coming off here is also going to be 75 pounds in tension. Okay? And so we're going to have an X and a Y support reaction at the pin to counteract both of these. So we'll have, we'll call this one BY. And we'll call this one BX. Okay? And now let's do C. It's going to look a whole lot alike. All right. We know this is T, so this is T. And so similarly to here, I'm going to draw these ones a little different, but it's the same thing. We've got CX, and we've got CY. Easy as that. And now let's jump back to part B. Put them all together on just this empty frame. All right, so let's start over here from B. We're just going to be seeing the opposite reactions that we saw at the pulley pins. So BX is going to be facing this way. Okay, BY is coming down here. BY, BX. Okay, this was our 75 pounds of tension. All right. And now, you know, this 75 pounds was hanging off over here, but as far as the frame's concerned, that's all happening at the pin, so we don't worry about that down there. Okay, we've got our tension. And then we've got our CY and our CX. Draw it like that. Okay, and again, you know, we don't even have to worry about D here because D's not part of the frame, and all that tension here is being counteracted with CX and CY. So then all we're left with are the support reactions at A, which we got in part A, which are AY AX. And that's the whole free body diagram. So I went a little out of order here. Feel free to do that on your tests. I'm the one grading them. I just think it's easy to think about the pulleys before you go back to the machine and put in the reactions from the pulleys. All right, so in example 617, it just wants us to determine the components of the reaction at its supports. So what supports do we have? We've got a roller at C, so that means we can only have a vertical support. B is not a support, that's just a little pin joint. And then at A, here's a component that we haven't seen in a little while. Since we've mostly been dealing with truss problems, we've had a pin joint and a roller joint, but this is just anchored straight into the wall. So you know that this A is capable of having, you know, an X and a Y as well as a moment about it, all right? So just keep that in mind. All right, so we have these two different components here, and we're going to have to break them apart and look at the free body diagrams of them separately so that we can solve this problem. So I'm going to start over here because looking at this, you can see that it's going to be really simple to resolve, because this 4 kilonewtons is directly down. We know we can only have a directly vertical support reaction at C, which means that we're just going to have another vertical support reaction at B. Okay, so we could do this by saying, you know, by taking the moment about B or the moment about C. Sorry, first let's resolve this into 4 kilonewtons per meter over 2 meters is the same thing as 8 kilonewtons applied 1 meter away. So, well, we can do, you know, we can take the moment about B and say it's going to be 8 times 1 minus 8 times 1 plus CY times 2, and then get that CY is 4 kilonewtons. And then you can say summation vertical Y is just going to be this minus 8 plus 4. Sorry, I'll go ahead and draw this in. CY equals 4 kilonewtons plus BY equals 0, which gets us that BY is 4 kilonewtons. Okay, so you can go through that, or in a situation like this, when you know that this is only vertical, you know that's only vertical, and you see that this is halfway between, you can just see the symmetry of it and know that B and C are both going to be 4 kilonewton supports. Okay, and that's it for member BC. So now we can go ahead and move on to member AB and use what we know from here. So we've got 4 kilonewtons positive applied at B. So that means that from AB's, this is from BC's perspective, it's vertical. Then from AB's perspective, you got equal and opposite. So here you've got 4 kilonewtons. Okay, we've got our 10 kilonewtons applied here is a 3, 4, 5 triangle with 3, 4, 5. All right, and it's this direction. So we're going to have, this is going to be 4/5 of 10. So that's 8 kilonewtons, okay? And then we're going to have this horizontal one, which is going to be 3/5 of 10, which is 6 kilonewtons. All right, cool. And so now we can figure out what the support reactions are going to be at A the way we would always do it. All right, so we can go ahead and sum up our X's and Y's. We've got -4, -8, plus AY equals 0. AY is 12 kilonewtons. Okay. We do our X's. It's going to be a -6 plus AX equals 0. AX equals 6 kilonewtons. Okay, and now last but certainly not least, got to remember that there can be a moment about A. So let's take a look at what we got. Looks like all the moment is trying to turn it clockwise, so we're going to have a counterclockwise moment at A. Let me go ahead and draw in AX real quick. 6K. All right, so summing our moment about A. Sorry, that's a summation. We have -8 times 2 minus 4 times 4 all right, plus our MA equals 0. That's 16, that's 16. So that gets us MA equals 36 kilonewton meters. All right, and so that's going to be in the counterclockwise direction. So, yep. So just make sure in this in frames and machines, they're bringing back other support reactions that we hadn't seen for the rest of the chapter. So just be careful that you don't forget about those. All right, our last problem for chapter 6 is going to be this fun pulley thing. Thanks for sticking it out with me, guys. I know that I've been kind of slow for some of this and that it took me a while to get these things up, but it's a learning curve. This is new for all of us. So hopefully I'll have chapter 7 coming out in a couple of days. And if there's any more problems that you'd like me to work, please just send me an email and I can do that. But anyway, let's go ahead and tackle this. So we see that, first off, there's only one cord running through this problem, that running through the pulleys, okay? So all the pulleys are hooked up to the same cord, which has a tension of P, okay? And you've got this little bit that's connecting pulley C and pulley B, and then you've got this little bit connecting pulley C to the ceiling. So, like we've been doing, we're going to draw some free body diagrams. Let's start down here at A, where we have this known mass. It's our only known in the problem right now. So let's draw pulley A. So we have 600 newtons, like this. And then we have, you can see that all three of these are the rope, or the cord, or whatever you want to call it. Okay, so this, and this, and this are all P. That's P, P, and P. And this is 600 newtons. All right, and so already we just have, we can figure out P just from pulley A, because we have, I guess this is summation in Y. We have 3P equals 600 newtons. So we have P equals 200 newtons. Okay, moving right along. Here, I'll label that. That was A. Let's take a look at pulley B. This little fella has some tension going up to pulley C. It has P and P from the cables. Oh no, I'm running out of lead. Okay, and that does it for this guy, which means that we can figure out T because we know P. So summing in Y again. We're going to say T equals 2P. Nifty. T is 100 newtons. T is 2P. 2 times 200 is 400 newtons. Okay. Finally, we've got pulley C. That was B. Pulley C. We have P.
We have P. We have T. And we have, we'll just call that R because that's what the book does. But this is what's connecting it to the ceiling. So, summing in Y. R equals 2P plus T, which equals 800 newtons. And that's it. These are all the free body diagrams. That's all the unknowns. Pulleys are have a sigh of relief when you see a pulley on a test because they really aren't too bad.